Hello, my name is Brent Bollert. In this presentation I will be giving a primer on hydrological modeling within the ECRI framework. We begin with its role in catchment management planning, and then move to an overview of the hydrological cycle, and then talk about the 5 steps in hydrological modeling, focusing in on basin delineation, a conceptual overview of the modeling approach, and calibration. So how do hydrologic models fit into overall catchment planning? The schematic off to the right here shows how historical climate and then general circulation model climate projections feed into hydrologic models and things like crop water demand models, which then are fed into water system models. The point here is that rainfall runoff from these hydrological models is a key component of the overall modeling framework that we're working with, because it allows us to translate precipitation and PET, which you've already learned about, into river runoff, which then drives things like performance of hydropower facilities available of water for irrigation systems and the like. Now, these models also allow us to estimate runoff in ungauged locations, and there are many ungauged locations that we're interested in, but if we have information on precipitation and temperature and other weather data, we can actually come up with runoff estimates in those locations. It also allows us to project runoff into the future. We haven't actually observed climate change yet, but with rainfall runoff models we can project what runoff will be based on these climate variables, and potentially extend runoff records and then generate synthetic hydrology, which I believe we can get into in a little bit more detail later, but the idea there is that we've only observed one history, and synthetic hydrology says, well, really we could have observed many different types of histories, multiple dry years in a row or multiple wet years in a row, and these types of models allow us to generate those types of time series even without climate change. So as a result, the point here is that these types of models are really central in the catchment planning process here. So what is the hydrologic cycle? We start off with some type of a land surface, and this is a simplified drawing here, where we have some sort of subsurface and then a river system, and the cloud upstream is representing our weather and climate. So we have our atmosphere, we have our precipitation that comes down from the cloud systems, and then there's some kind of interception that occurs within the trees and the other vegetation. And then there's surface store. Water actually percolates into the soil surface and enters the groundwater system. From the vegetation and also from open surfaces, we have evapotranspiration that occurs, so that's a demand as indicated by the color here. And then part of the water that comes down in the form of precipitation is converted into overland flow, which makes its way into the rivers. There's also infiltration that is entering into the groundwater system that can be converted into soil water storage, or through flow here, which is just water that's sort of flowing along downstream with the river system, but subsurface. And then we have percolation, and as percolation takes water from the soil storage system and moves it into the groundwater storage system, so quite a bit deeper. And then we also have groundwater flow. So there are these different layers of the groundwater system. There's the shallow groundwater system and the deeper groundwater system. And then we have return flow, so water that's actually moving from the groundwater system into the surface water system. And this is a key component of dry season flow in rivers, is what's called base flow. And then there's channel storage. There's water that's actually stored in the channels, and then there's channel flow. And what we're really trying to get to with our rainfall runoff models is what's happening in channel flow, which is an integration of overland flow, what's converted from channel storage into the channel flow, and then also return flow. And then we have our storage systems such as lakes and also ultimately the ocean, and we have evaporation off of those surfaces as well. And so now we move from the hydrologic cycle into a conceptual model of watershed modeling. So typical inputs that we have to this type of model would be topography, soil characteristics, land cover, and land use. Many of these things are available from online sources. They can be gridded, and we'll talk a little bit about that later. And also meteorological data. So these would be either gauge data that give us information about precipitation and temperature, and depending on how you calculate potential evapotranspiration, we might also be interested in wind speed, humidity, pressure. We also have gridded data sources, and these are very helpful when we're trying to do analyses of hydrological models and hydrologic processes at watersheds that don't have gauges. Now, typical outputs of hydrologic models include stream flow or runoff, potentially subsurface flow, and also depth to water table. Now, the focus of the work we're doing here, and most of the work that we do in general, really focuses on that first point, which is stream flow, as opposed to the other two, which typically involve a more detailed groundwater model. So what are the steps in hydrologic modeling? The first is delineation of the watershed, and then moving on to obtaining hydrologic and geographic data, selecting the modeling approach that we're going to go forward with, and then calibrating or verifying the model that we're working on. And in fact, calibrating and verifying the model we're working on. Those are two different steps. And then using the model for assessment, prediction, and design, which is ultimately our goal when we're designing these types of hydrologic models. Now, we won't go into detail on all 5 of these steps, but we will focus on steps 1, 3, and 4. So starting with basin delineation, there are a total of 7 major river basins across the continent that are included in the ECRI analysis. Nested inside of these 7 basins is 463 subbasins that were delineated using detailed topographic information. These 463 subbasins are provided in the form of GIS shapefiles on the data warehouse. Okay, so as an introduction to selecting our model, the first step here is to look at the basis for many of the hydrologic models that we're going to be looking at. So all are governed by a hydrologic budget, where in simplest terms is simply inflows minus outflows equals the change in storage in the system. So this is just the continuity equation, as it's called. So inflows, the major inflow is precipitation, and that can come in the form of liquid precipitation or snowfall. And then we also have groundwater recharge. And then outflows from the model include transpiration from plants and also evaporation from both plant surfaces and also lake and other surfaces. And then we have stream flow leaving the system, so that would be an outflow of flow. And then groundwater out. So in addition to groundwater entering the system, we also have outflow of groundwater. It all depends on the dynamics of the groundwater system. Now overall, this equation in the bottom provides us a very, very broad and generic formula for the types of inflows and outflows and how those translate to a change in storage. And in this case, that's suggesting a change in either some storage reservoir, meaning we physically have a reservoir in the system like what's shown here, or it can also, from a modeling standpoint, be the change in storage in the soil system or in the groundwater system more broadly. So next we move on to the 4th step in the hydrological modeling process, and that's model calibration. The rainfall runoff model that was used in the ECRI work was called WATBAL, and that's actually a model that is built into the program WEEP. This is a schematic of the Volta River Basin in that software program WEEP, which is Water Evaluation and Planning. Now typically calibrated rainfall runoff models use observed data to tune and adjust the model parameters until the modeled runoff is equal to observed runoff. Typically we use inputs such as precipitation, temperature, and other meteorological variables to drive runoff so that we don't actually need to use observed runoff or rely on observed runoff when we run the model under the climate change scenarios. We can actually use climate change projections to develop runoff using these models. Now, typically to do calibration, we need naturalized runoff, which means runoff in a system with no human demands or infrastructure that controls the management and allocation of water. Here, we only had gauged runoff available. So in this project, we actually did not have naturalized runoff available. So instead, we relied on gauged water flows in the rivers. And these gauged river flows were inclusive of upstream demands and upstream reservoir management, meaning that they were not directly the result of natural processes. So as a result, calibration was used using WEEP, meaning that a schematic much like this for each of the river basins, with each of the gauged flow points at various locations of subbasin outlets, were used to essentially adjust the calibration parameters by running a managed water system. That process, in turn, generated a set of tuned calibrated models that were then used subsequently to generate projected runoff under a variety of different climate projections. In this primer on hydrological modeling in the ECRI framework, we started with its role in catchment management planning, and then focused on an overview of the hydrological cycle, and then turned to the 5 steps in hydrological modeling, starting with basin delineation, an overview of the conceptual approach to modeling, and finally, model calibration. Thank you for your attention.